Who didn't get an email from me last night?
You.
Well, if you didn't get an email from me, it doesn't matter. But if you didn't, please write your name on a bit of paper that's coming around. The reason you might not have got it is if you're direct entry and you're not fully registered yet, or you're direct entry and you haven't updated the student lists yet, or you have changed year for some reason, or God knows what else, administrative balls up. So if you didn't receive an email from me last night about the Amplifier Lab, then I need your email because I have no way of getting it. Yeah? Right, okay. As a quick straw poll, can you put your hand up if you didn't get it? Oh, it's not too bad then. Started somewhere over here. Where, who was the, so if you can pass it to the guy in the glass and a couple of rows back. Those of you who just come in, if you didn't get an email from me last night, can you write your name and your email address on the bit of paper that's going round? So when we met yesterday, we were discussing the Amplifier Lab, which is bearing down upon you like a juggernaut. No, it's going to be a great thing. And this is the board that has been prepared, and I said a few things that are quite important that I might have forgotten, so I'll just say them again. When you're soldering on this board, I've made all the thermal masses of the things a bit big, so the soldering iron needs a little while to warm them up. The idea is that if you still believe that soldering is like a gluing process, where you put some solder on the iron and then you kind of wipe it on the joint, in the hope that it might stick, which it isn't at all that. This will force you into a different way of doing it, because that definitely won't work, and what will happen is you'll be able to just pull the component off. So make sure you hold the iron on there and get it hot first. That's the most important thing, because if you don't get past that, any electronics that might happen is not gonna. One other thing, these needle meters were the cheapest ones I could find. But I had to buy an awful lot of them, so they were still quite expensive. If it sticks, just tap it. It's traditional. If it still sticks, then you can wheedle the side off with a screwdriver and realign the back face underneath. It's engineering. Real engineering. Right, good. So we were in the midst of a discussion about a circuit which I screwed up at the end of the last lecture, so I'll redraw it. And it was for day 2, and it looked something like this. Is that big enough? Okay. Ah, there's a mistake. Gone now. Try again.
Udah tengok ini. Suruh dia masuk.
And when we stopped talking yesterday, we more or less finished with the integrator, which is this bit here. And this bit here is a trigger, 2 Ds, and there are some Xenodides, and the Xenodide breakdown voltage in reverse is 4.3. But in forward bias, it's just a silicon diode. It turns on a silicon PN diode, and it turns on at 0.7 volts. And I had a graph as well, and the graph was a graph of what I hoped to get out of this circuit. So it was a function of time, and it's an oscillator, so it should make the signal. And I said I wanted triangle and square. So we'll try and put in a square and a triangle. Do you want red, black or green for the other one? Green. Green it is. And we said that for this business here, this node is virtual earth. We're happy with the virtual earth idea. The op-amp uses the feedback to maintain this point close to the non-inverting input. Since that's grounded, this also looks like ground as well. Because the input impedance of the op-amp is very high, all this in 118, you need to see it again, there is no current flowing in that pathway. Consequently, any current here must equal any current leaving there. So if I put a known voltage across the resistor R, I can charge up the capacitor C with a known current. Yeah, that's the integrator essentially. But I don't actually want to use an integral equation to make it go. I will use a differential equation instead. You know there's a video, right?
Yeah.
Okay. It'll go on YouTube. So I said that the frequency should be 1 kilohertz, and that the output voltage should be, sorry, if I go down, plus or minus 5 volts. So this is going to be plus 5, this will be minus 5, and this distance here should be 1 milliseconds worth, because it's 1 over a kilohertz. So we also said that for a capacitor we have a differential equation, and that it was I is C dV by dt. So I'm going to try and get to my I, or maybe I'm going to pick a C and then work out what the I is, or possibly I will change the I into V upon R, and then I'll get RC, and that'll be a time constant. You can attack it however you like. I'm just going to go and pick the C, because I know what's in the lab, yeah? I'm telling you now, the only C choice you can make is 100 nanofarads. Don't bother to write that down or anything. Just write it down. Because it's not anywhere else except here. So I'm going to choose this. C, not C1, it's C, isn't it? It's 100 nanofarads. Because it's the only one that's in the boxes. You get lots of resistor choice though, don't panic. I'm not taking away your freedom. The reason I want you to have a bit of freedom in the design is that it makes it slightly more realistic, in the sense that when you have to solve some of your problems, you will have a lot of choices available to you. And if that's a new experience, then we didn't do our job of training you very well at all. So you have a little bit of choice. But if I were you, I'd choose 100 nanofarads. Assuming you can do the calculation, so you choose a value that's not 100, you work through it, and you get some consistent values. When you turn up at the lab, that's fine. You'll just have to quickly redo them for 100 nan. But since you can already do them, it won't take you long, right? Well, that's the theory anyway. So I'll choose my C. What is my dV? 10? Did I hear a 10? Who did I hear a 10 from? It was you and you. This is going to be a slow day. Do you want a biscuit? No. Yeah? Biscuit? No biscuit? You? Right, good. We're alive, yeah? Do I need to sing at you like yesterday? Is that what it takes? Whatever. Right, you want to be careful. I'll sing the music I like, and that won't go down well. Right, 10 volts. 10 volts because we're going from plus 5 to minus 5. So my dV is 10. What's my dt then? Any advance on a millisecond? Half a millisecond. Can you agree? Yes. Do you want a biscuit? I can tell that I'm going to give the biscuits to my PhD students today, aren't I? Righto. So we've got. All right for right here? So we have I is 100 times 10 raised minus 9 times 10 over 500 times 10 raised minus 6. Somebody do it on a calculator, will you? Now. That's 8. 1 over 5 is usually 0.2 something, and I've got 5e minus 8 on the bottom, so you don't really need to calculate it, but what about that? You're like a load of bears pouring at the calculator trying to get the buttons. .002. Hang on, I need to write that down. So 2 milliamps. 2 milliamps. 2 times 10 raised minus 3 amps, or 2 milliamps. Right. If you're not finished with this one, come grab it at the end. Or I'll put it up in a bit. So I've got my I is 2 milliamps, and I had. So I is 2 milliamps, and I've got between here and there, this will either be 5 or minus 5. The reason I know it will be that is because if this one is reverse biased, it will break down at 4.3, and if this one is reverse biased, this one must be forward biased because I put it the other way around, and consequently it will have across it 0.7 because it's a forward biased PN diode, and 4.3 plus 0.7 is 5. So I know there'll be 5 here, plus or minus, I don't know, but definitely the magnitude is 5. And I know that here I have 0 because it's virtual earth, because of the reasons I said about the op-amp and feedback and high internal gain and blah blah blah. In 118 if you need it. So I know across R is definitely 5. Plus 5 minus 5 makes not a lot of difference reading. So if B is 5 and I is 2, what's R? 2.5 kiloohms? Yeah. 2.5 kilo. So now you know what R is, because I told you what C is. So you could, if you wanted to, go back and work out what the time constant is and choose from different R and C's. But there's only 100 nan in the box. Happy with that? So we are finished with the integrator now, even though we didn't ever use the integral equation. If you want to use the integral equation, you can. It just runs it. You get the same answer in the end. Yes.
I'm not really happy with the graph, so because for some reason, how does the Schmitt trigger switch just at the peak of
We will come to it.
the so
We will come to it. It's the next one. You think you should switch at 0?
around
We'll see in a minute. So, integrator I finished with. Oh, sorry. So now we will worry about the trigger circuit. Don't forget, there is no negative feedback. There is positive feedback. The only thing that you can say about this for sure is the op-amp equation still applies, and that the input impedance is high. There is no virtual earth. This point will not live at 0. Well, it will cross 0 sometimes, but you can't assume its value. You can work it out. So, looks like an amplifier though. That is cool. I've taken out R3 just for a few minutes for a bit of simplification. let's imagine that, let's imagine we're running from 5 volt rails as well, because then it actually makes it. We won't, it's 15, but the Sedra diodes will take care of it for us. Let's imagine I want this to switch state when it gets to 5 volts. So this is going to go from either +5 to -5 when this hits -5 or +5. If that's the case, I know that all the op-amp will do is V out is AV, V plus minus V minus. So V out will get really, really big or small, depending on the difference between V and V out, V plus and V minus, sorry. And it will manage that because AV is enormous. Let's assume AV infinity. We won't do any real calculation. So, when is V plus going to hit 0? Well, if I let R2 and R1 the same value, and I call them potential divider, because don't forget there is no current going in here. So whatever current's in R1 is also in R2. So really R1 and R2 are a potential divider of V in and V out. Now I want V in to get to a certain magnitude, right, and it will switch V out to its other state, which also happens to be 5 in magnitude. So the relationship between V in and V out in terms of size, or the magnitude, is 1. They are going to be equal in size. As a consequence, I can say, well, this point needs to be 0 to make the switch happen, because it's going to, as this falls through 0, it will become smaller than this and the op-amp output will drop down. As this becomes slightly larger than 0, the equation applies and the op-amp output goes up. So I'm heading towards a situation where it switches when this is 0, but I want this to have magnitude 5 and this to have magnitude 5. So I do have a 0 in the middle, but it's not a virtual Earth. And it won't stay 0 for very long at all, only at the point where the switching happens. So what have I got across here? Now I know if you're with me or not. This will switch when this is 5, and when it switches, that's 0. So I've got 5 less 0. It's 5? Yes, no? Perhaps. That's going to be 5. If this is going towards the other version of 5, -5 say, let's imagine that hits plus and that goes to minus. Well, this is still 0 when it switches, so at the instant that it switches, I will have also 5 across there. Remember, this is heading towards -5, so this arrow really is on this end. Otherwise, you'll end up subtracting the voltages from each other, and you'll say it certainly doesn't do anything, which isn't right. So, I know they've got the same voltage across them, and I know that they must share a current, because there's no current going off down here into the op-amp. So R is the same, V is the same, R is the same. So R1 equals R2. That doesn't actually give us a value. You must choose the current, but there are some other considerations to be had to do with the rest of the circuit and how much current is actually available. So we will deal with it in a bit. If you don't like the sound of this, the way to clear it with your conscience, if you like, is to do a few test cases. And your test cases can revolve around a graph, which can look something like this. Let's imagine that this is an edge, and this is the so the triangle is green, the square is blue, and we are looking just at the very top of the pulse. We are sort of sat in this region up here, zoomed in a bit. And you can put some numbers on if you like, because you know what they'll be. This will be +5, and let's make that 4, 3, 2. And you know that I've drawn the graph wrong is what you know. So, the conclusion is R1 equals R2 for the trigger. So now we've got a value for R and a value for C, and we've got R1 and R2, but we don't know what they are yet. But we do know they're equal. If I go back to my original diagram, I've got certain current pathways out of this trigger circuit. I've got a current pathway that does that. Red okay? Big enough. I've got a current pathway that does that, and a current pathway that does that. And the op-amp has to supply them all. And there's a certain limit of current that you get out of an op-amp before it decides it doesn't want to play anymore. Any thoughts what it might be approximately? Yes?
About 20 million.
About 20 million, more or less, yeah. About 20 million. You will find if you can drag 20 million kicking and screaming out of an op-amp and you put your finger on it, it will get hotter as you hold your finger there because you're insulating the op-amp and it's having a hard day. So it'll get warmer. So you think it's getting hotter, it's getting hotter, it's getting hotter. Let's switch it off. You switch it off and then you think, but it's not blown up. I'll have to switch it on again, otherwise I can't proceed. Switch on, and it'll be working, and you'll be measuring it thinking, it's not blown up yet. Why hasn't it blown up yet? And you put your finger in, it's getting hot, and you turn it off. So, we won't go all the way to, would you like a biscuit with 20 milliamps? Righto. What's got into you lot? You're not sick, are you? Gone off your food. So, if I said this point here is going to go up to plus 15 down to minus 15, it will do that because the op-amp will go all the way to its rails, and the rails in the circuit are plus minus 15. This point here I know is going to be plus or minus 5. So I know across the resistor I've got how much? 10? 10. And this resistor I told you is a kilo ohm, so the current in the resistor is 10 milli, which is half of 20. So it's not going to get too hot when you put your finger on it. So I've got to share out my 10 milliamps because that's all that's available, and if I don't share it out appropriately, the circuit won't work properly. I've got to provide a certain number of milliamps to charge up C through R. It's 2. We come to it earlier. So I've got 2 milliamps going down there. I've got to provide a certain amount of current for this trigger circuit to have some positive feedback because there must be a current in R2 and a current in R1 and we agreed they would be equal. And all the rest, an unknown quantity, goes down into the Zener diodes. You can't work out what the current is by some numbers. The only way you can work it out is by saying it's what's left after you've decided all the other things. The reason is the diode characteristic is heavily non-linear and working out would require, well, some exponentials or a repeater. So shall we pick a code for this feedback network? You've got 10 available, you've used 2. Come on, pick a value, guys.
500 micro.
100 micro.
500 micro.
In advance of 500. It's fine, you can choose that value and it'll probably work, but I'm heading towards a particular one that I know will work. And I also know there's 2 of them in the kit because I put them there.
3 milliamp.
3 milliamp. Could do. Let's choose a value of 4.7k. Right, so that's just over a milliamp, yeah? Just over 1 milliamp. If it was 5.1k, it would be just under a milliamp because we agreed 5 volts across them both. And I know there's 2 of those in the kit because I spec'd it. But if you want, there's 2 10Ks as well, and I think there's 2 100Ks. And I'm pretty sure there's 2 1 meg, but if you use 1 meg, it probably won't work because there won't be enough current to actually. There is a tiny little current that goes there, and you must supply it, but we just assume that it's negligible. Because if you use an enormous resistor, this negligible current will become quite a large fraction of your feedback current, and that will mean that your feedback won't act in the way you expect it to because you've got this big error term. So try to pick something in the range of a kilo ohm to about 50 kilo ohms, and you'll be all right. It's a pretty good goal for op-amp circuits generally, actually. So if I have, what is 5 divided by 4.7, by the way? 1.2 something. No? 1.06. I was way off, wasn't I? 1.06 milliamps. So what does that leave me from my 10? 6.94 milliamps, is it? So 6.94 down there. Happy? You can pick some other values if you want, but that's the way it works. I'm not really worried about you actually calculating the values. I'm worried about getting you to think about the whole circuit, how the bits interact with each other. All of this is pretty much in the video, although I don't think I actually gave you the answer. I'm not too worried about you having the answer. It's the thinking that's important. The other day of the lab, any questions about that before I finish on it? Stumped into silence. So third day is a bit more transistor type stuff, and we'll make a small power amplifier, although it's not like a real bra amplifier, it's 100 milliwatts, so it's sort of small power. And the calculations that are involved they're not worse, they're just different. There's two experiments. The first experiment is to do with crossover distortion. Are you familiar with the term or not? It's probably not come up in lectures because I haven't said it. Right, in that case, and have a read about crossover distortion. You'll find it in the chapter about transistors. The second lab is a sort of the second experiment is a mechanism of getting rid of the crossover distortion. And you have to do a little bit of circuit design to set up a current which flows in a transistor. So I'm just going to draw the circuit, but it is in the lab sheet. And if you got my email last night, the lab sheet has been slightly corrected because I missed out a few crucial pieces of information. So we've made it a bit harder than it really should have been. Essentially, you had to watch the video to pick up the other little bits of information, but I didn't want to make that clear, so I put those in the lab sheet now. So if you did get my email last night, you have the latest lab sheet. So the circuit looks like this. I would advise you not to copy it down because it's quite lengthy. Much better to just listen to my voice and fall asleep. So we're back in amplifier land, and this amplifier's got a gain of 20. I know that because it says in the lab sheet. What value should I pick for resistors? 1K20. What gain will that yield? 21. So I'll pick 1K and 19, except 19 is not in the lab, but I will pick 20 after all. And I'll end up with a gain of 21. That drives, we've got a resistor here, which I think is 470, I think it's 470 ohm. Ah, perfect size. So this A is the ammeter, which is the needle meter on the board. That one. And you can know some values. That's 10 ohms, that's 10 ohms. That was a capacitor there, C1. And a load resistor, which is R. And that's 100 ohms. And it's a 2 watt resistor, or it's a 1 watt resistor, sorry. But we're going to dissipate 0.1 watts in it. So on the lab sheet you'll see it's got a watt in there. That's the maximum power dissipation, or maximum rated power dissipation. It's not the actual value of power we will dissipate. It doesn't really matter what these values are. All this stuff in this red box is soldered onto the board already. And I can show you show you this for a minute, if I can take that away. Contrast all right? Yeah? Yeah. Can't zoom out anymore. So, transistor here is the top transistor. This one is the bottom transistor. The stuff in this box here is the stuff in the box on my bit of paper, which I'll put up in a minute. And then I've got two transistors here which form the output stage with two 10 ohm resistors that are already on the board. And there is the posts are connected under the board to various bits and pieces, and the white lines which are drawn on the top on the silk screen tell you where those connections are. I've tried to put most of the connections that are to do with the... If it's got a white line, I try to put the trace on the top, but there are lots of other connections to make it go, which go on back. So if I turn it over, it probably won't focus. So there's, all this stuff is power, essentially, and things for LabVIEW, because I've connected up all the LabVIEW stuff as well. So if you finish early, it's a big if, I know, but if you finish early, and you fancy fire up the computer, you can do things like get the collector current for a transistor and get the voltage across it, and then multiply the two, and look at the waveform for the power dissipation in the transistor, and wonder why it's not sinusoidal, if you want. If you finish everything that's on the sheet. So I thought, just to give the lab a bit of life. Notice, by the way, a bit of PCB design, all these traces go that way. And all these traces, more or less, do that. It's really handy because I can never run into a problem where I've routed something that I need to go around. I can just drop to the other side and change direction by 90 degrees. The only difficulty with this is you end up with a lot of vias. Happy with what a via is? No? A via is, so, see if I can zoom in without it going out of focus. Oh yeah, it's big electronics. Now I've just got to find a via. That is a stupid level of zoom. I should take this back to the lab and use it as a microscope. Right, see this? Now I've got to find out which one it is. It's this one, isn't it? Look, wow. So that little gold ring there is the via. And what it does is it connects this trace here, which is the output of this op-amp, which is enormous. Wow. It's quite something, isn't it? It's a pity you can't read the text that's on. There is text, but it doesn't show up. This connects to the trace on the other side of the board, which is going that way. That's what they're for. So if you decide that you're going to route your board with horizontal and vertical traces, the trace is another word for a wire that's on board, you won't minimise the number of vias because you will have to change side a few times, probably. Whereas if you route it round now and then, you might be able to avoid the vias, so many of them. But when you start routing round, you may later try to route something else nearby and think, oh, I've boxed myself here. So it depends. Also, it makes a nice, neat looking board. Right, quite enough of that. We wouldn't want to teach you to read electronics, would we? So, back to this. So this is the top transistor, this is the two output transistors, and this is the current source. And your job is to decide what the value of R6, R7, and R5 are. And it says in the sheet that you must choose this current here, and you can choose between 2 and 5 milliamps. So I'm going to make it 6 in order that I get different numbers, so that you can't use my numbers, because that'd be plagiarism and I have to come and get you. I'm very busy and I don't have time to come and get you all. C1 we'll come to later. Again, all this is in the video, so if you don't like the speed I'm going or you want to hear it explained differently, then I'm explaining in the video as well. So, let's look at the DC conditions first and see what's going on with that. My feedback is connected up here for this op-amp. in practice, I can also connect a feedback to this node here if I want to, and then I have feedback around all these transistor stages and the op-amp. And the op-amp will use its big open loop gain to try and correct deficiencies in this transistor circuitry. But that's towards the end of the lab. Right now, I just want to talk about a bit of DC and what happens to the signals. So let's assume we have the feedback only around the op-amp and all this stuff, no feedback. It's going to do what it's going to do and we have to like it. It says in our spec that we must... That's okay. Power is 0.1 watts. Somebody needs to be a bit quick on the calculator because there's only about 15 minutes left. Not even that. 0.1 watts. So what voltage will I end up with across RL? V is V squared over R. And this will be R and S. So then V squared is equal to power is, so that's RP, or PR. R is 100 ohms. P is 0.1 watts. So V squared is equal to 10. So V is 3.15 something. RMS. V RMS. VP is therefore 4.47 something. I multiply by root 2 because it's just like that. So here is root 2 involved. Happy with this? It's EEE 117 stuff and things. Good. So I know that on this node here, I have a signal which at the very least has 4.47 there and 4.47 minus 4.47 there. Yeah.
Sorry, square of them is 2.16.
3.16, not 1.5. Never mind.
You have to do something there. V squared is 10, so V should be 3 point. That's 3.
Alright.
I thought it has 2 there.
I rounded down in my head, apparently. No, it's 3.15 I've got there, and 4.47 is the peak. That's a 7, that's a 7. Back to my DC conditions. Well, if I've got no input, because that's when I've only got DC in my system, what's this going to be? This amplifier put no input? No output? No output. 0. This is a forward bias PN junction. Voltage? 0.7. 0.7. So this must be a minus 0.7 because I dropped down one diode drop. Right. I've got another diode drop here, and this base is connected to this emitter. Yeah. So here I drop down to minus 1.4. So let's imagine. Right? Okay. Good. We'll carry on in black. Let's imagine this current that flows from the top rail to the bottom rail is 0. Is about 5 milliamps. It says so in the lab sheet as well. You actually get to change it with the little potentiometer in the middle. But let's imagine it's 5 milliamps. Now, 5 milliamps passing through 10 ohms is 5 millivolts, 50 millivolts, a number of millivolts, 50 millivolts. It's not much, is it? It's quite small. Probably neglect it.
Yeah.
Probably. So we won't worry about the voltage dropped across here, or the voltage dropped across here. And this is a PN junction, which is also forward biased because it's a PNP transistor. So if I was at minus 1.4 here, I'm ignoring the voltage drops across these small resistors. Their use, you can read about if you want. And I've got another 0.7 here, so by this point I'm down to minus 2.1. Yeah. All right. So at the top of this business here, which is a current source, I'm at minus 2.1 volts. The other thing I know about this lot is it's all emitter followers of current sources. This circuit, whatever you do to its base, its emitter will follow minus 0.7, hence emitter follower. It can provide a big current through this pathway, controlled by a small current through that pathway, if you like to think about things in terms of current gains. If you prefer, you can say a small change in voltage here controls a big change in current here. Your decision about that. So this has a gain of 1. the voltage gain is 1. Whatever voltage I put here, I'm going to get here less than 0.7. This one is same configuration. This one, also same configuration, except PNP transistor now, so all the voltages are flipped. This must be higher than that, not the other way around. This one, on the other hand, what I'm going to do with this, I'm going to try and keep this current constant, and I'm going to do that to provide a very good load for this emissifier. So whatever happens with the emissifier, this should attempt to keep its current more or less the same. Of course, it won't be able to swing because of the signals, but at the moment, it should be fixed. So if I've got minus 2.1, and I know that my signals in this system must all be this size, how did I come to that conclusion? Well, I just told you that all the transistors have a gain of 1, voltage gain. So if there is no gain in any of this business, whatever signal I got here can't be any bigger by the time it gets to here. That's quite a key thing. It takes a long time to get the hang of. So I'm at minus 2.1, and I know that on this node, I must swing plus minus 4.7. So minus 2.1, going up to, what is it, 2 point something something something, and down to minus 6 point something something something. Because my DC and my AC is superimposed. You can do the superposition of DC and AC signals, as was in the last question of the exam in the last part, where I had a couple of inputs into an op-amp, some are AC, some are DC, and I get you to do the superposition in 118. Remember? Like a Vietnam thing, is it? Running for cover. Now, I tell you what, if you ever want to test a subwoofer, Apocalypse now, about an hour in when the helicopters land, it's got a really good bass. Of course, if you've got a ripped off copy, it might not be as good. Just to keep Sony happy. So the lowest this can ever get is minus 6. This is really important because if I allow this collector to go below this base, I will have 2 switched on junctions. And if I have that, my transistor will be in saturation, and then it won't be an amplifier anymore. It will be a switch which is switched on. And that's really bad because I'm trying to make an amplifier. So the